Assalamualaikum warahmatullahi wabarakatuh. My name is Mubin bin Nur Azmi, and I'll be presenting my research report, which is numerical simulation of an ocean current turbine operating in Wakefield. First and foremost, I would like to apologize if there's any distraction from me because I'm a little bit sick. Okay, uh, I'll be going straight forward to the abstract. So the abstract is an ocean current turbine OCT numerical simulation for creating, testing, and tuning flight and power takeoff controllers, as well as for farm layout optimization is presented. This simulation utilizes a novel approach for analytically describing oceanic turbulence. An approach for integrating wake effects into this single device numerical simulation is presented for predicting OCT performance within a farm. To accomplish this, far wake characteristics behind a turbine are numerically described using analytic expressions derived from wind turbine wake models. Turbine wake is characterized in terms of increased turbulence intensities and decreased mean wake velocities. These parameters are calculated based on performance of the upstream OCT and integrated into the environmental models used by downstream OCT. So the next one, we'll be going to the introduction of my report. So ocean energy has great potential for reducing carbon emissions in the long term because ocean energy technologies do not generate greenhouse gases GHG in operation and have low life cycle GHG emissions. One method of energy production from the ocean is utilizing ocean currents for in-stream hydrokinetic electricity production. An ocean current turbine (OCT) is a device that converts ocean current energy into electrical energy, and prototype OCT development is now approaching the offshore testing stage. So the problem statement of this research, weeks of upstream turbines can greatly affect the power produced by downstream turbines and the loadings on these downstream devices. Although an initial turbine array layout for a specific flow direction is designed to ensure that downstream turbines are out of wake, fluctuation of flow direction can be expected in ocean environment, which may lead the downstream turbines to fall into the wake of upstream turbines. Wake models for these devices are required to determine four optimal positions of turbine in an array and to obtain necessary information required to build flight and power takeoff control algorithms that will move downstream turbines out of wake of upstream turbine. Okay, my research objectives is the primary achieved objective documented in this dissertation is the creation of a numerical simulation for calculating the performance of an OCT operating in the wake of an upstream OCT. These simulations accounts for waves, current shear, and ambient turbulence, as well as the wake of an upstream turbine. The previously developed simulation of a single OCT was extended by incorporating ambient turbulence and wake effects into the numerical models for simulating the performance of a downstream turbine. Okay, so the literature review. Numerical simulation approaches utilized for OCTs have many similarities to those used for wind turbines. Therefore, existing wind turbine and OCT simulation tools are reviewed. Since the eventual goal of this dissertation is to contribute towards array optimization in an OCT farm, wind turbine farm modeling approaches are summarized to understand how individual wake models are used for farm modeling. Ambient turbulence affects the performance of both wind and in-stream hydrokinetic turbines. The instantaneous power generated by a marine turbine in a turbulent open channel flow has been found to be highly modulated by the turbulent features of the flow. Therefore, it is important to incorporate ambient turbulence effects in turbine simulations to accurately predict both power production and turbine loadings. Okay, so for my research methodology, the purpose of this chapter is to investigate the approach for numerical simulation of the ocean current turbine operating in a wake field. In addition, this chapter will compile all of the methods information to retrieve the results of the research. Okay, so there are two proposed methods in this research. So the first one is ambient turbine simulation, and the second one is downstream turbulence characterization. So there's actually more methods that can be used for this research, but for me, I will just only use two of it. Okay, so for ambient turbine simulation, this chapter presents an approach to simulate ambient turbulent flow based on turbulence statistics. An approach similar to TURBSIM is taken as velocity spectra is utilized to calculate instantaneous velocity. Results of simulation are presented and discussed. In general, a turbulent flow can reach a statistically stationary state if the data time history is collected for a long period of time. A velocity component u can at any time t can be expressed as the equation shown below, which is ut equals to u mean u plus ut, where u is the time average mean velocity in the directional flow and u prime t is fluctuating component of velocity associated with this direction with zero mean. So the continuous PSD for wave number k has following proportionally in inertial subrange, which is the given formula below, where gk is continuous PSD expressed as a function of wave number and E is turbulence kinetic energy dissipation rate. Okay, so for a given frequency f, the wave number k is directly proportional to frequency, which implies the power spectral density gf as a function of f can be expressed as gf equals to epsilon 2 over 3 f power of negative 5 over 3 times with u bar over 2 pi powered by 2 over 3. For a given turbulence intensity I, the dissipation rate is a constant, and if U is also taken as a constant, the above equation can be rewritten as the equation below. Gf equals to AF powered by negative 5 over 3. Okay, so the standard deviation and the integral of one-sided PSD SF in frequency domain can be related by uh, standard deviation square, which is variance integrating from 0 to infinity GF by DF. So turbulence intensity in the direction of flow can be defined as I equals to U RMS divided by U bar. So plugging in the standard deviation equals to I times U and GF equals to AF powered by negative 5 over 3 into equation above. The constant can be obtained by integrating the right hand side of the equation from considered minimum frequency to maximum frequency as the equation shown. Okay, so for the next part which is downstream turbulence characterization, this chapter proposes empirical expressions to quantify downstream turbulence behind an OCT. These expressions are based on similar expressions for wind turbines, but tuned to match published experimental data available from in-stream hydrokinetic turbines. So results using the proposed expression are presented and compared with published experimental data. So experimental data of downstream turbulence at centerline and radial locations are available from in-stream hydrokinetic device models. So the following equation is proposed to model centerline turbulence intensity behind hydrokinetic turbine to match experimental data available in the equation shown below, uh, where delta I equals to 1 over 5 over I power of 0.15 C 0.40 times by S over D powered by K, where K is equals to negative 2I powered by 0.1. The centerline turbulence intensity IC is then calculated as IC equals to square root of delta I square plus I square. So turbulence at radial location of the hydrokinetic turbine centerline is observed to be Gaussian, and therefore a Gaussian equation is considered to model downstream turbulence at radial location. So first, a turbulence parameter IP associated with centerline location is defined as IP equals to IC minus I over I, and the turbulence intensity IR at radial location R from the centerline with corresponding turbulence IP is then defined as IR equals to I uh, multiplied by IP exponential of negative 3 R over D square plus 1. So results from equation above are compared with available centerline downstream turbulence data. Figure below shows comparison of calculated turbulence intensity from the equations with experimentally measured turbulence intensity. So as you can see from figure below, the left side is shown for ambient turbulence intensity of 3%, whereas the right is for ambient turbulence intensity of 13%. So in the next figure, it shows that it compares calculated and experimental data available where the ambient turbulence intensity is about 7%. Okay, so published data were used to model downstream turbulence were different from experimental setups, as the purpose of equations presented on the slides before this are to estimate the order of downstream turbulence in general without being specific to any 64 experimental condition. Data for downstream turbulence at different radial locations are also available. So figure 3.3 or figure 3.3 is actually this figure below compares experimentally measured data with downstream turbulence calculated. Centerline downstream distances are held constant at 7D, which is the left one, and 10D, which is the right one, and the ambient turbulence intensity is 3%. Okay, so the next one is for the research discussion. The studies in this research used numerical simulations to evaluate the temporal and spatial water velocity variability using the method discussed in the proposed method. For the ambient turbulence simulation, time histories for a single spatial node are presented to display the temporal variability of the water velocity, while the instantaneous water velocities over the swept area of the rotor are presented to show the spatial variability. For the downstream turbulence characterization, it is noteworthy that the prediction accuracy for radial location is dependent on prediction accuracy for centerline. Therefore, the differences between experimentally measured and calculated downstream turbulence in the last figure is not only due to accuracy prediction for radial location, but also due to the accuracy of the centerline. Okay, so for the conclusion of this research, numerical simulation of a downstream OCT is carried out to evaluate its performance by taking into account wake effects caused by an upstream OCT. And the next one is analytic expressions to quantify added turbulence at a far wake region 5D and beyond behind an OCT are proposed. These expressions are developed to best fit existing experimental data that measures turbulence behind in-stream hydrokinetic turbines. Okay, so there's also some recommendations for further studies. So the first one is effects of wake on OCT can be evaluated by considering more than two turbines at an upstream and or downstream locations. So for the next one is vertical axis in-stream hydrokinetic turbine were shown to be more sensitive at low turbulence frequency where 5/3 law may not be valid. Therefore, relationship between frequency and velocity spectra at low frequency can be examined. So uh, that's all from me. Thanks for watching.